So in today's lesson, we looked at three different problems where we're to make a conjecture about them. And the first one that we had a line L with a ray R coming off of it, and two angle bisectors. And the conjecture that we were supposed to say was that these red dotted lines made a right angle. But to help us do that, we needed to label the drawing. So it's not enough just to say line L and line R. So we're going to put some points on this. We'll call this point M, and we'll call this A, B, C, and D, and E. So capital block letters for points. And now I can label the angles. So my conjecture is that the measure of angle BMD is equal to 90. We're saying that this is a 90-degree angle. That's the conjecture. And to prove that, well, we'll prove that here in a minute. Here we have a circle M, with a diameter of AB, and point C is on the circle. And when we moved this around and we measured it, we noticed that it's 90 degrees. And so the conjecture here would be that the measure of angle ACB, notice we use the middle letter as the vertex for each of these cases. The measure of this angle is equal to 90. We think that this is a 90-degree angle. You could say angle ACB is a right angle. That would be a conjecture. And notice how this is already labeled for us. Here we have the drawing, and I could label this M and A, B, C, D, but I'm going to try to do it with shorthand. I'll say that this is angle A, angle B, angle C, and angle D. And my conjecture here is that angle A is congruent to angle C, that these two angles are the same. That I can't just mark it and say that they're the same. I want to prove it. So these are conjectures. A conjecture is a statement that you believe is true, but that has not yet been proved. So let's prove each of these. In this one, again, I'm going to use shorthand. I will say that this is an angle bisector. Let's see. So if it's an angle bisector, that means that angle AMB is congruent to angle BMC. These two angles are congruent. I can mark them with a tick mark. I can also mark them with an X. I'll just call this X and X. They're the same because this line, this ray, MB, cuts this into two equal angles. We can also say that angle CMD is congruent to angle DME. And why is that? Well, because ray DM was defined as an angle bisector. And I'll use two arcs here to show that these are the same. And I'll call this Y. So to do my proof, one way to do this is to show that the relationship is that they all sum to 180. That is that x plus y is equal to 180, or 2x plus 2y is equal to 180. If I divide everything by 2, I get x plus y is equal to 90. And that is what I wanted to show, was that this angle BMD, which is x plus y, is equal to 90. Here we have a circle, and we know that the radii of a circle are congruent, so I have two radiuses here, two radiuses here. And this forms a isosceles triangle. It looks like it might be equilateral, but I can move this C anywhere, remember, but this will always be isosceles. And we know that the base angles of an isosceles triangle must be the same. So we could call this X, we could call this X. Here, this is also an isosceles triangle, and its base angles are the same. We'll call this Y and this Y. Again, we know that the measures of a triangle sum to 180. So we have x plus y is equal to 180, or 2x plus 2y is equal to 180. And that means that x plus y, which would be our angle ACB, is equal to 90. Again, we've proved this. And here we have this relationship. We know that A and B form a straight angle. A straight angle is equal to 180. That is, A plus B is equal to 180. B plus C is also a straight angle, so that's equal to 180. So C plus B is equal to 180. If I subtract B from both sides of these equations, I get A is equal to 180 minus B, and C is equal to 180 minus B. And these are the same. So if I have 180 minus B is equal to 180 minus B, that means that A is equal to C. And so that is the proof of these three theorems. What I want to not lose on you is the beauty of using transformations as well. I could have taken a point here and rotated around this midpoint 180 degrees. So this point A would become A prime if it's rotated around point M. This point B would become B prime if it's rotated 180 degrees around point M, which shows that this angle must be the same as this because of a rotation of 180 degrees. Rotations or transformations take points to points, angles to angles of equal measure, or segments to segments that are congruent. So here we have an angle that is being rotated 180 degrees, takes it to an equal angle. In this one, if we were to rotate this angle by y degrees, I could end up with two angles, one of them being x and one of them being y, and this one here being x and being y. So I have two equal angles, 1 and 2, that divide a straight angle. And since by rotating this, I can see that I'm going to have two angles that both have an x and a y in it. X and a y, and put this y over on this other side. This will be an x and a y. And by doing that, I can see that each of the angles must be 90. I haven't figured out a transformation that would get me this angle yet. Maybe if I take and draw a parallel line, extend this line. This angle could be translated up to here, so this would be x. And if I were to rotate this segment around its midpoint, this could be y. So by rotating and translating, I can see that I can also get it 2x plus 2y is equal to 180. So I guess what I'm saying is that not only can you do the problems with algebra, so like I've done down below, but you can also do this with transformations. We could rotate this 180 degrees. We could translate and rotate around the midpoint to get a straight angle. We can translate or rotate this y to get an x plus a y and an x plus a y, two angles that are the same that divide a straight angle in order to do our proof. So the different ways of proving it. Now we have proved the vertical angles theorem, so you can write this down, that vertical angles are congruent. We've also proved that if you have a straight angle in an array, that the angle bisectors formed by those two angles forms a 90-degree angle. And this is called Thales Theorem, named after Thales of Miletus, somewhere in Turkey, modern-day Turkey, 350 BC. He proved that if you have a diameter and a point on the circle, that the point on the circle would be a right angle formed with the diameter and a triangle. And that's the big idea from today. Good luck and success.